And autonomous vehicle and machine learning applications. I'm Randy Machemehl, professor of civil engineering, University of Texas, and I'll be the moderator. Our first speaker is Dr. Steve Boyles. He's a professor here in University of Texas at Austin, civil engineering department. Steve's one of my favorite guys in the department because he's so willing to do whatever the department needs. And I can go on about that for a long time, but Steve's a great guy and an outstanding researcher. He's going to talk to us today about assessment of parcel delivery systems using unmanned aerial vehicles. Steve?
Great, thank you, Randy. So let me, oops, it looks like I'm not allowed to share my screen. Is that permission that I need to be given?
Perfect. Can you give Dr. Boyles the right, please? I think should be able to, right? We have a tech support behind. Just 1 second.
Oh, Boyles, you can share your screen now.
Okay, great. Okay. Okay, so is everyone seeing my slides?
Yes, sir.
Great. And how much time do I have, Randy?
About 20 minutes.
Okay. Okay, yeah, so this project has to do with logistics using unmanned aerial vehicles or drones. And so the title that you've got here is a little bit more specific than the title that's in the program. It's a little bit about the specific ways that Tenquo, my PhD student, and I formulated this particular logistics problem involving drones. And so I'll get into this. Feel free to ask me questions all the way through. I'll describe the problem, the mathematical formulation, how we solved it, and then some experiments that we did. So the idea behind this, there have been a number of articles lately about the use of UAVs or drones to help out in logistics. Partly this is in urban areas, they are not subject to congestion, whereas delivery trucks they're stuck on the roads. This is part of a larger trend towards electrification in freight. This is partly for environmental reasons and even for financial reasons. As the price of electric vehicles are dropping, you're seeing some logistics companies that are looking at using electric vehicles as parts of their fleets. And so the problem that we were looking at is a logistics problem involving deliveries using electric vehicles and also using unmanned aerial vehicles in coordination. The idea is that this drone could be carried on and launched from the vehicle to assist it as it's doing its deliveries. And in the literature, this is sometimes called like a flying sidekick vehicle routing problem, where the drone is it's launched from the vehicle, it takes care of some deliveries, and then it rejoins the vehicle at a separate location. And so this is the problem that we are studying here. So it's a vehicle routing problem, specifically a traveling salesman problem. We're going to assume that all the customers need to be served either by the drone or by the electric vehicle. And yeah, the electric vehicle serves as a hub for the drone. The drone launches from there, it's retrieved there. And this is kind of the interesting assumption that comes about because of electrification. So because the vehicle is operating off of a battery, it may need to visit charging stations along the way. If it's doing a long route over the course of a day, it may need to recharge. We're also going to assume that this electricity is shared with the UAV. And so the idea here is that the UAV can charge while it is on the electric vehicle. So it can, and while it's doing so, then it's taking the electricity from the electric vehicle and using it to charge the UAV battery in between flights. For the experiments we do, the assumptions we're making are that these charging times are not super long. What this means for the electric vehicle at the charging station is that we're assuming some sort of battery swapping setup rather than a charging setup where the electric vehicle would have to sit for a while, but rather the battery would just be swapped out. And yeah, so the assumptions that we have, all of the customers need to be served once. Charging stations, however, could be visited multiple times. And this is a complication that raises some issues with the typical solution methods. The usual algorithms that are used for TSPs or for vehicle routing problems assume all the customers must be served once and only once. The charging station nodes, however, they don't have to be visited, or they could be visited, or the same one could be visited more than once. It's possible that the electric vehicle might charge somewhere, do some deliveries, and then come back and charge at the same station en route to the rest of its route. So, and I've already talked about the other assumptions, that the electric vehicle and the UAV share their electricity. And this essentially just means that the UAV can charge from the EV battery. So this is an example of what our routes might look like. So in this example, there are 6 customers. 0 is the depot. These solid lines represent the route of the truck, and these dashed lines represent the flight of the UAV. And so notice what happens is that the UAV, it's launched at a particular node, it delivers its package to a customer, and then it flies back and has to link up with the electric vehicle or the truck at a different node. And so this means there has to be some coordination that's involved, right? The truck has to be there when the UAV gets there. There are distance limits on how far the UAV can fly, and so on. But at this node, it can launch again, make a separate delivery to a single customer, and then come back again. And so these are the kinds of tours that we're coming up with. It's a coordinated route involving some nodes for the truck, and then these sorties that the drone flies to do deliveries to additional customers. So mathematically, I'm not going to talk about all of this notation in detail. I'm just doing this to kind of cover the main parameters that we have to keep track of. So we have travel time costs for the truck. EV is the truck, electric vehicle. UAV is the drone, unmanned aerial vehicle. So notice that the travel times between pairs of nodes may be different for these vehicles. For instance, in a grid network, the electric vehicle would have to follow the road network, and so it would have to drive along the grid, whereas the UAV in an unobstructed environment could fly directly there, and kind of looking at the, as the crow flies distance. Of course, in a dense urban area, the UAV may not be able to fly just in a direct path, but we're still allowing for the possibility of different travel times. These vehicles travel at different speeds. The UAV is not subject to congestion, and so forth. There are range limits, both for the UAV and the electric vehicle. There is a certain amount of time that's needed for launching and retrieving the UAV. And so these are the main parameters that we have to set up this model. The decision variables, the primary decision variables are the route taken by the electric vehicle, which we'll represent with X, the drone sorties in addition to that, which we denote by Y. And the rest of these decision variables, this is essentially bookkeeping, keeping track of the order in which customers are visited, how much charge is left at different points along the routes, what time are we at along these routes, and so forth. But X and Y are really these are the main things we're trying to decide. Everything else is just bookkeeping around that. And so our objective is to minimize the time it takes to conduct all of the deliveries. So this T sub Z plus MS plus 1, this is the time at which the vehicle and the drone return to the depot after conducting all of the deliveries. So we want to conduct all of these as quickly as possible. But as I mentioned, there's some bookkeeping because the drone and the truck have to be coordinated along the way. They're not routing independent of each other. And so this is captured in some of the constraints that we have. So I'm not going to go through the math on these. I'm going to talk about these constraints. There are a lot of constraints here. And so I've kind of grouped them into 3 main categories. So this first set of constraints is associated with the routing of the two vehicles, making sure that customers are visited exactly once and only once, making sure that the tour starts and ends at the depot, making sure that the tour is connected, that there are no subtours, coordination constraints, making sure that if the vehicle enters a node, it leaves a node, and so forth. So this is the group of constraints that makes sure that the X and Y variables represent a coherent route. The route's connected, the drone is always launched and retrieved from nodes when the truck is there. It's only serving one customer in between, and so forth. We have a second set of constraints that's associated with the electricity and the electrification parts of the problem. So we've got constraints on our bookkeeping variables about the amount of charge remaining as we go. We've got a constraint to represent the charging that happens when the EV leaves a charging station, and similar things with the drone, just making sure that there's enough charge between visits to the charging station to do all of the, to service the route as it's been specified. These are the coordination constraints, which I alluded to earlier, making sure that the travel times stay in sync. Now, if the truck gets to, if there's a node where the truck is supposed to retrieve the drone, if the truck gets there first, then it has to wait for the UAV to arrive before it can continue on. And so we've got a set of constraints to represent that as well. We have some ordering constraints. This represents the flight range of the UAV, and making sure that the vehicles are visiting nodes in the order that the X and Y variables say. And finally, we have just the domain constraints. The X and Y's are binary variables. The delivery times need to be non-negative, and so forth. So this is the problem that we've set up. Now, this is a tricky problem to solve for a few reasons. So traveling salesman problem, as we all know, these are hard problems to solve even as it is. But now we've got two vehicles that have to be coordinated. And furthermore, there are range limits and visits to charging stations and so forth that have to be accounted for as well. So to solve this problem, we came up with a three-step heuristic, and decomposing the problem into three main steps. And the main idea is that the problem becomes a lot simpler if we decide which nodes are going to be served by the truck and which nodes are going to be served by the drone. If we have a procedure that works in that case, then we just need to start, then we can start playing around with these sets of nodes. Which nodes are served by the truck, which are served by the drone? Can we maybe swap nodes between these sets? If we have a good way to solve the problem, once those two sets are fixed, then this gives us a way, kind of an angle of attack on this problem. So for now, assume that we've decided which customers will be served by the electric vehicle and which vehicles will be served by the drone. So then step one is to solve the EV TSP. This is an electric vehicle TSP. This is a problem that's separately been solved in the literature. There's no drone, but there are battery constraints and charging stations. So, okay, fine. We've figured out which customers are going to be served by the electric vehicle. Find the TSP tour through them with visits to the charging stations. Then we try to find ways to insert the nodes that will be served by the drone into that existing route. Is there a way to do so that satisfies the range constraints, that satisfies the battery constraints, the coordination constraints, and so on? So this is our heuristic once we've figured out which customers are going to be served by the truck and which are going to be served by the drone. Of course, that just kicks the can down the road to that question, right? How do you figure out which customers are served by which vehicle? If there's a small number of customers, you can just enumerate them all and see which ordering works best. For large instances, that's not very possible. And so what we did in those cases, well, so we started with some small examples where we were able to enumerate all the solutions. And we looked for features of those solutions. What proportion of nodes tended to be served by the drone? Were there other characteristics of nodes that tended to be served by the drone? And so we use this as a jumping off point. So rather than having to enumerate every possible partition of customers between these two vehicles, we can start with configurations that look like configurations that seem to work well. And so in our experiments, we saw that the best results happened when 30 to 40% of the customers were served by the drone. And so this is where we started. And so then once we go through these 3 steps for that partition of customers, then we can start modifying it in other ways. We look to see, are there customers that look like they could save us some time if we served them with the drone instead, or if we just gave them back to the electric vehicle. And so then we do a local search from there. So our experiments, the main experiments I'm going to show here are computational. We also did some sensitivity analyses to the parameters that go into this problem. There's nothing really too surprising there. As you increase the range limit, then you can get faster deliveries and so forth because it gives you more flexibilities in the routes. The computational comparison was the main thing we were interested in, just because this problem is tricky to solve. So we started by comparing the performance of this heuristic that I just described. First of all, with an exact solution using Cplex, a commercial solver, and these are on some small instances that were randomly generated. So the way to read this table, the way that these cases are labeled, 5C means 5 customers, 2S means 2 charging stations, 2R means that we're modeling up to 2 visits to the same charging station. Now, this is a very small example. This is not a realistically sized example. This is just to give an idea of the difficulty in solving this problem. Throwing it to Cplex, which is a state-of-the-art commercial solver, takes minutes to hours to solve even a problem with just 5 customers, whereas our heuristic operates in less than a second. There is a little bit of an optimality gap. The solutions that our heuristic gives are not exactly optimal, but it gives a solution in well under a second, whereas Cplex takes close to 40 minutes. And so, when we apply this to a larger instance, this has 10 customers. Our approach is still able to give answers in well under a minute. Cplex is not even able to find even a feasible solution in over 2 hours. And so that's why this column is all NA. We cut off Cplex after 2 hours. It was not able to even find a single solution that worked. And so even going from 5 customers to 10 is a significant jump in complexity because this is a combinatorial problem. The number of orderings of customers increases factorially. And so this is just a tricky problem to solve. We also looked at a real world case study based on a network in downtown Austin. So in this example, there are 25 customer nodes. So this is significantly larger even than these examples that Cplex was unable to solve. So we had 25 customer nodes, 10 charging stations, and we set up the travel times. We used the Google Maps API to get travel time estimates between these nodes during the peak hour time on a typical Monday. And so when you look at the route, this is what it ended up looking at. The circles here represent the locations of the customers. The triangles are the locations of the charging stations. The solid line, as before, is the line for the truck, and the dashed line represents the flight of the drone. And so you see there's a lot of visits that are being made. The drone is kind of flying all over the place as the truck is proceeding with a few visits to charging stations. And we found that there was a fairly significant reduction in the amount of time it takes to serve all these customers because you have this flying sidekick to help you out along the way. So just to wrap things up, the main work that we did under this project from CAMMSE, we came up with a formulation for the electric vehicle traveling salesman problem with drone. People had done TSPs with drones before. They had done TSPs with electric vehicles before. But to our knowledge, we were the first to combine these two things into a single problem. We came up with a heuristic method for this. This problem is completely intractable to solve exactly, but we found a heuristic that gives solutions in a reasonably short period of time, and at least on the small instances, was within 15% or so of optimal. And we've shown that this gives, the heuristic can be applied even to a practical problem on the scale of Central Austin. So with that, I will wrap up. I am happy to take any questions at this time.
Thank you, Steve. Any questions? Anybody?
I have a question if
Yeah,
Go ahead.
okay, yeah. So Steve, you said that the computational complexity was much higher in the case of a 10 customers side, and you had to interrupt the simplex solver. So can you estimate how larger? You said that it was growing what, exponentially, or
yeah. So if you just look at the number of candidate solutions, that number is factorial in the number of customers. Now, if you do some clever dynamic programming, you can get that down to exponential, but it still grows very quickly, both in the number of customers and also in the number of charging stations, because the charging stations can be placed, their visits can be anywhere in the routes of customers, and they may not be visited, or they may be visited multiple times. So,
okay.
Yeah.
And so here the 7,200, it was not even getting a feasible point.
Yes.
Okay.
Yeah.
So it's very far away from converging, of course. Yeah. Okay.
Any other questions? All right. Thank you, Steve. Great presentation. Enjoyed it very much.
I'm glad to present our work here.
All right. Our second presentation will be given by Dr. Wei Fan, who is, of course, our leader. And we all know Wei very well. He's going to talk about extreme gradient boosting XGBoost model for vehicle trajectory prediction in connected and autonomous vehicle environments. Wei?
Okay, thank you, Dr. Machemehl. Can everybody see the screen I shared just now?
Yes, sir.
Okay, great. Thank you. So very glad to present some of our the work we did. You can see the second author here listed. Pengfei Liu is one of my PhD students. Just defended his dissertation work last month. So congratulations, Dr. Liu. And this is part of his dissertation work. As you can see, the title here is Extreme Gradient for Vehicle Trajectory Prediction in Connected and Autonomous Vehicle Environment. So here's the outline of my presentation. I will introduce you maybe to the field of CFE, and then talk about the data we used, and then the methodology we developed using XGBoost, and then some of the results we would like to share with you. And then introduction here. As you can see, connected autonomous vehicle, we can share the position of the vehicle, the speed and acceleration rate of the vehicle with other vehicles and also with the infrastructures. So a lot of researchers and practitioners expect that the CFE will significantly improve the safety and mobility of our transportation system in the future. And obviously for connected vehicle, the technology-wise has been well tested in the last 10 to 20 years in terms of DSRC technology. And 5G obviously is on the horizon. We're going to see the speed going to be much faster than DSRC. And then the V2V and V2I, which means vehicle to other vehicles and vehicle to infrastructures, the data can be shared automatically. And then V2X, which means vehicle to scooter, to pedestrian, to any other traffickers, of any mode in the transportation system. And then we talk about autonomous vehicle technology. We talk about that the vehicle can be operated without direct driver input in terms of controlling the vehicle, steering acceleration, deceleration, and also braking. And as we all know, that autonomous vehicles use a combination of sensor technologies to realize the autonomous driving, which could include radar, LiDAR, cameras, and GPS, and so on. And the automated driving system can analyze the data collected by all the sensors and then put them together and fuse the data and then decide what the next step going to be in terms of whether the vehicle should accelerate or decelerate, in terms of car following and also lane changing. The vehicle can make a decision itself whether should join the platoon, maybe in the left lane or right lane or in the current lane, how to follow other vehicles and things like that. So as we all know, the SAE classified the autonomous vehicle into 6 different levels, from 0 all the way to 5. And we're talking about pretty much at least level 3, which means autonomous vehicle, and if there's something goes wrong on the roadway, and then the driver can take over the vehicle. And then 4 and 5, which obviously are more advanced. 5 is purely autonomous vehicle. And then we talk about technology here on these slides. We all know the radar can work under all weather conditions, and they can track the presence of the other vehicles and their directions and also speeds of any object using the radio waves. And the good things about radar technology that it works under all conditions in terms of storm, fog, snow, anything. And then we have a LiDAR. LiDAR basically, it's kind of like a technology that has extreme accurate depth perception information, can collect all those informations and can generate the 3D map whenever whenever we need. And then we have a camera which have a highest resolution and collect all the detailed information about vehicles, pedestrians, and even pavement markings, all those surroundings. And the cameras are best for training machine learning models, but as we all know, it's not that good for calculating the depth perception, and it can also not work well in bad weather conditions as well. Now, this slide gets to the data we used for kind of like training the XG boosting model. So the data we use is called NG SIM data, which is next generation simulation data set. As we all know, this is a website managed by Federal Highway Administration under US Department of Transportation. And the data available, they're made freely and publicly available. And the data we use is on US 101, which is near LA, California. And we use June 15th, 2005 data. And we have 3 periods of data have been collected in the past. The period we use is between 7:50 a.m. to 8:05 a.m. And a total of 1,993 individual vehicles were selected. And of course, we have a lot of data steps, and also in terms of car following and lane changing and all that, because the data set basically they transcribe the vehicle trajectory data from the video. And in the SIM, we have a lot of vehicle position, speed, acceleration rate, and also headway information available. And in this project, our goal is trying to predict the acceleration rate for the subject vehicle, which we all know is the determining factor of a vehicle trajectory. So just trying to show you, give you some idea about our work here, some background information. As we all know, on freeway, a lot of mainline lanes, we have a leading vehicle, subject vehicle, and then we talk about X, which means the coordinate of a front and center of the vehicle in feet with respect to the leftmost edge of the section. And then we talk about Y, which means the coordinate of the front and center of the vehicle in feet with respect to the edge section of this freeway. And then we have a speed as well, V. And then we have SP, which means the spacing between the front center of two vehicles. And then we have the leading, the position of the leading vehicle, and also the Y coordinate of the leading vehicle as well. And then also, obviously, we have the speed of the leading vehicle, and then acceleration as well. And then we're getting to the methodology part. So as we all know, to model the connected autonomous vehicle, a lot of researchers have adopted the model developed by Treiber and many others back in 2000. And this model is called IDM. It's called Intelligent Driver Model. They adopt the model and apply them in Vism software like Vism and Sumo and software like that. And then these basically slides present two equations they used in order to calculate the acceleration rate of the subject vehicle based on its own speed, position, and also the position, speed, and acceleration of the preceding vehicle just in front of the subject vehicle. And then the algorithm we used to develop our model is called XG boosting. As we all know, this method is fairly new, which was developed by one of the researchers graduated from University of Washington back in 2006. And his name is Tianqi Chen. He works right now in Carnegie Mellon University. So XG boost algorithm is a very popular boosting tree algorithm. Right now, it's widely employed in industry because of its accuracy and also highly efficient in predicting. And then the model can be, the objective function can be presented, by two components. The first component, as you can see, is sigma L, and that things represent the loss in terms of the misprediction. And then second part is omega. That omega basically translate to the complexity of the model. So as you can see here, we have basically two components. One is talking about the model prediction accuracy, and the other one is talking about complexity. So oftentimes we must strike a perfect balance between the two. If we need to develop a model that are really accurate in terms of a prediction, then often, more likely than not, our model probably will overfit the training data set. And then on the other hand, if the model, we have a lot of layers, a lot of parameters that we include in the model, then the model might perform well, but it's not simple at all for use. And then the variance may be pretty high. It's not that stable in terms of the prediction. So we have a trade-offs here. And then XG boosting basically use the Taylor series, a Taylor expansion of the objective function to calculate. They take the first derivative, second derivative, and then they get to kind of like a weight on each leaf in order to calculate the score of the leaves, and then sum them up they get the final prediction. So the model comparison we used is root mean square errors, and the second one we used is mean absolute errors, called MAE. And we compared basically the observed value and the predicted values here. As you can see, this table give us some idea about how well XGBoost can perform compared to the IDM model we typically use in order to model the connected autonomous vehicles right now in the research domain. As you can see, boosting algorithm outperform the IDM in terms of both performance index here. And then these slides basically should give you some idea about the predicted and observed values in a prediction horizon of 30 seconds. As you can see, the XGBoost algorithm still outperform the IDM model as well, and also very close to the actual data we collected by NGSIM database. And then this slide basically talk about the feature importance. So what do we mean by feature importance is this. If a feature which is kind of like analogous to the variable we use in the past in terms of linear regression model and maybe logistic regression model, those basically talk about independent variable. But in XGBoosting, it's kind of like a feature. So the more a feature is used to split the node to generate for splitting more nodes, and then the higher the feature gonna become. As you can see here, this figure will tell us the relative importance of 8 input features in the XGBoost model. So as you can see, longitudinal position, lateral position, and velocity of the subject vehicle are among the 3 most important features to predict the vehicle trajectory. So with that, I'll be glad to take any questions that you may have. So obviously we have a lot of work. We cannot, present all of them, but we're just trying to make it simple. If you're interested, we can communicate after the presentation. But right now, I can answer any questions you may have.
Well, I'm not totally familiar with the data set that you used, the field data set, but I think it's freeway data. Is that correct?
Yes, sir. That's called an NGSIM data set.
Right.
The next generation simulation.
I wonder, what would be your expectation of your model if the data that you were comparing it to was in say a grid network arterial street system where there's traffic signals and all that? Is that a next step in the testing process possibly?
Yeah, possibly, because right now that's a great question. The NGSIM data set deal with the freeway and arterial. For this particular case study, we have like a 650 meter, about 2,100 feet data set, which is arterial. And yeah, in the future, maybe if the data is available, particularly for signalized intersection or unsignalized intersection, that would be hard because a lot of times, depending upon the traffic and a lot of other factors, maybe become much more complicated.
Yeah, I would think so.
Yeah.
Any other questions? Thank you, sir. We appreciate it very much. Excellent presentation.
Thank you.
All right, let's see here. Our next speaker is Dr. Nicholas Lownes, professor, University of Connecticut. Nick is I believe you're an associate chairman in civil engineering now. Is that right? Nick?
Yes, sir. Actually, I just stepped down this year.
Okay.
Yep. It was a victim of the pandemic. Because my duties now include being a third grade, seventh grade, and eighth grade teacher as well.
Yeah, no, that's quite a task. Nick is going to talk to us today about prioritizing people, mixed equilibrium assignment for AV based on occupancy. Nick?
All right. All right. My slides coming up?
Yes, sir.
All right, great. All right, so yeah, we're looking at a mixed equilibrium assignment for autonomous vehicles based on occupancy. We call it prioritizing people because it's kind of a shift from some work that's been done recently, looking at ways to implement control strategies for autonomous vehicles using some modeling paradigms that are going to be familiar to most people, I think. I want to acknowledge my PhD student, Sruthi Mantri, who's been doing all the heavy lifting on this project, and my colleague, David Bergman, who is an operations research professor over in the School of Business. So our focus is looking at minimizing the impact of empty autonomous vehicles on occupied vehicles. So prioritizing the people in the network, regardless of whether they are driving their own vehicles or whether they are in an autonomous vehicle. And most, I think most researchers acknowledge that there's going to be a fairly long transition time when we're going to have a mixed fleet on the network. And so this is looking at, say, the next 20 to 30 years as we transition to having autonomous vehicles as part of the vehicle fleet. And it's using a kind of, a straightforward, at least conceptually, concept is a differential route assignment for occupied versus unoccupied vehicles. User equilibrium for occupied, system optimum for unoccupied. With the idea being that we want people to be able to continue to minimize their personal travel time, whereas unoccupied vehicles can absorb some additional delay by taking perhaps a little bit more circuitous routes. And today I'm going to show you our proof of concept application, which is on this, the well-known Sioux Falls network. And we are currently in the process of transitioning to a larger application, the Eastern Massachusetts network. Both of these are from the Transportation Test Problems GitHub repository. So our model and solution method is adopted from a paper by Zhang and Ni back in 2018, where they were looking at the trade-off between system efficiency and control intensity by assigning all autonomous vehicles using a system optimum framework and all human-driven vehicles with a user equilibrium framework. And they use a diagonalization algorithm to perform this mixed equilibrium assignment. And so we're tweaking this concept just a bit. So all of their autonomous vehicles were assigned using a system optimum, whereas we are making the differentiation here, not based on the level of autonomy, but based on whether or not a vehicle is occupied. Some other research in 2018 by Zhang et al. Suggests that with the introduction of autonomous vehicles, that up to 18% of households could own fewer vehicles if an autonomous vehicle was available to serve multiple trips within the household, where it could take mom to work, return home, and then take the kids to school, or take dad out to a to the store to get groceries. And so there's a possibility that There could be a reduction in household vehicle ownership with the introduction of autonomous vehicles. This also has the knock-on effect that there could be a 30% increase in VMT, up to a 30% increase in VMT by unoccupied vehicles making these return trips throughout the day. And so this creates a potential conflict where the benefit to households of owning fewer autonomous vehicles could be impacted if we're sending unoccupied vehicles back to make these multiple household trips on circuitous routes, because you can't get back home to take the kids to school if we miss that pickup window for the kids. So what we're looking to explore here is the trade-off between these two things. So adapting this mixed equilibrium model and then seeing what the effects are on these return trips for unoccupied vehicles, and then developing a method of addressing this to make sure that these unoccupied vehicles can get back home to make these additional trips. And so, yeah, our research question, can we do this? So first we were investigating whether or not this is an issue if we adopt this framework, and then implementing a method of reassigning vehicles that violate this pickup time tolerance. So what we're going to do is assign unoccupied autonomous vehicles using an SO assignment and occupied vehicles using a UE. And so for those of you that might not be familiar with these two models, these are the formulations of user equilibrium and system optimum. Assignment models, for those of you familiar with Sheffy's 1985 text, these are pulled from his work. And from a modeling perspective, we're not making a dramatic shift in the formulations. Essentially, we're just seeing that travel times are now impacted by both occupied and unoccupied vehicles. The difference being that the occupied vehicles are given priority. They are assigned to their preferred routes first, and then system optimum vehicles or empty vehicles are assigned subsequently. And these two models are, so these assignments are done sequentially, and this continues until convergence, essentially. And so this, the methodology that we implemented is, and I'm not going to go into great detail on it because Zhang and Ni do a fine job in their publication providing detail for this diagonalization algorithm. And the four basic steps I just mentioned were occupied vehicles are assigned first as user equilibrium. They can't do any better by shifting their paths. And then, given that the state of the network after the occupied vehicles are assigned, unoccupied vehicles are assigned using a system optimum. Update travel times and then reassign in that order, and we repeat this until it converges. This can be thought of as a diagonalization of the Frank-Wolf algorithm. And Sheffy showed that if this converges, then it could be, should be an equilibrium solution to the UE assignment problem with asymmetric link interactions. And as I mentioned, our application is on the Sioux Falls network, relatively small network. I believe it's 26 nodes. And what we do is we are looking at varying percentages of the demand being either occupied or unoccupied vehicles, using Frank-Wolf for the UE assignment and using the Barron nonlinear optimization solver for the SO assignment. And this is all implemented in Python. And so I'm going to show you a graph here that shows the impact of the percentage of occupied vehicles on total system travel time. So over here on the left-hand side, this is all unoccupied vehicles. And since this is being these vehicles are being assigned with a system optimum framework, we would expect, and we see that with all unoccupied vehicles, it's a system optimum assignment, and the total system travel time is minimal. And as we increase the percentage of occupied vehicles, we see a fairly linear trend, as we would probably expect, shifting all the way up to all occupied vehicles. So the current condition, or essentially the current condition, where every vehicle has a driver, and we see that total system travel time goes up to the full user equilibrium assignment. And this, this trend and these results, agree well with the Zhang and Ni results, and we would expect that, because at this point the difference in what we're doing is really just conceptual, where we're, instead of just looking at the percentage of autonomous vehicles, we're looking at it as the percentage of occupied vehicles. And where we start to see some interesting results is if we're thinking now about the effect on occupied vehicles, we can then look at the individual trips. And so in this table, again, we have the percentage of occupied vehicles on the far left-hand column. And what we see is that in the second column, that roughly 50 to 60% of OD pairs see a reduction in their travel times when we are assigning unoccupied vehicles using the system optimum. So we're seeing that improvement. We're seeing a decrease in total system travel time, as we would expect, as the percentage of occupied vehicles goes down in the third column. The next two columns are just showing the percentage of the OD pairs with 1 or 2 minute delays in their travel time with respect to the shortest path. The second to last column is showing the average delay for the occupied vehicles, generally around 1 minute. And the final column is the maximum delay with respect to the shortest path for occupied vehicles. And so we see in this far right column, that the maximum delay for these occupied vehicles runs from about 2 to 4 minutes. Now, if we compare this to unoccupied vehicles, so again, far left column is showing the percentage of occupied vehicles. And as we would expect, a fairly high percentage of the unoccupied vehicles, that should be percentage of unoccupied that have a higher travel time than occupied. So we would expect that that would be the case for most OD pairs. I think the most interesting column here is this far right column, where the max delay for these unoccupied vehicles can sometimes reach almost 40 minutes. So there are some vehicles that within this framework, even though the total system travel time is going down, there are some of these vehicles that are being assigned to very circuitous routes. And as I mentioned at the beginning, this could have implications for the households that are using these autonomous vehicles. If it's an additional 20 minutes to return to the home to pick up a passenger for the next household trip, that could have serious impacts for that household. Either they're going to have to invest in another vehicle, or people are going to run late to school, or they're going to be unable to make some of those trips during the day. And so what we wanted to do was impose what we're calling a pickup tolerance, and not allow these overly circuitous routes. And currently what we're doing is a fairly straight ahead implementation of this, where we're identifying those vehicles that are exceeding this pickup tolerance, and shifting them from the system optimum group to the user equilibrium group. And so when we impose this pickup tolerance, when we impose or this shift, moving those vehicles exceeding their threshold from the SO to the UE set, what we see is that we're able to, in this Sioux Falls network, so we're able to implement this so that none of the users have more than a 5-minute delay. And that was our pickup tolerance for this small example. So we're able to do this with a relatively small impact on total system travel time and delay for user equilibrium users, which was great. So we saw a slight uptick in the maximum delay for user equilibrium users, but it wasn't really very substantial. And we see two different cases here. One where we have 90% occupied vehicles. The second example is for 10% occupied vehicles. And again, so the occupied vehicles do see a slight uptick in their delay, and there's a slight uptick in the total system travel time, but nothing that was incredibly substantial. Now, one of the issues that we've run into is that the implementation as is, the runtime is on the order of 27 hours. And this is for a gap and step size as shown on the bottom bullet point. And those do have a significant impact on computational time, of course. And one of the things that we've been trying to zero in on is the balance between solution quality and runtime. If we don't impose fairly strict gap and step sizes, we see funky results in the solution where we wind up with some very strange total system travel time results. And so these are what we've zeroed in on, but they do impose a fairly significant runtime. And what we're currently working on and moving toward in the future is an expansion to the Eastern Massachusetts network, which is about 3 times the size of the Sioux Falls network. Because of the pandemic, these have been implemented on a relatively small machine. A lot of this Ruthie has been implementing on her laptop, which no doubt impacts our computational time. So we're in the process of shifting this over to a server, Dr. Bergman's server over in the School of Business. And with a longer term application to the Hartford network, where we can also integrate with some household travel demand data that we have from a statewide travel survey we did a few years ago, and their vehicle ownership characteristics. At this point, I'd be happy to take any questions.
Hi, Nick. I've got a question.
Sure, Steve.
Yeah. So I found your comments on the gap really interesting about needing to have that a gap of 10 to the -4, and you were seeing funky results otherwise.
Mm-hmm.
So one of my PhD students is actually looking at exactly that issue of what gap do you need. There was the famous study by Dave Boyce and Hillel Barguera that said 10 to the -4 is what you need for the link flows to stabilize. We've been seeing like the aggregate measures, like the total system travel time, stabilize a little bit earlier at like 10 to the -3. But our setup was obviously different than yours. We weren't looking at a multi-class thing with automated vehicles. This was just for the standard traffic assignment problem. So I was just wondering if you could say a little bit more about what different things you saw. You said you saw funky things with the TSTT, and I'm just curious what effects you were seeing.
Yeah, so the effects that we were seeing, what we found was once we hit about 50% occupied vehicles, we would see a very nonlinear trend, and up around 70 or 80% occupied vehicles, we would see the total system travel time exceed the user equilibrium threshold up there, which was very counterintuitive, of course. And so we would see somewhere around here, we would see this trend go up over the user equilibrium line and then come back down and converge with 100% occupied vehicles. And
so that blue line wasn't stable at all then?
It really wasn't. And especially once we started getting to about 40, 50%, we were seeing things kind of destabilize.
Oh, that's really interesting. Is there a paper on this? I'm curious to read some more about what you've done.
Yeah, we are working on it, and the goal is to submit by December. But we've also got a bunch of just results that we have along the way that we can certainly share with you.
Yeah,
just show you what we found.
That'd be great.
Yeah.
Yeah, and I can share some of the experiments we've been doing. But I find this really interesting. So,
Oh, great! Thanks.
Yeah.
All right, sir. Thank you very much, Nick. Excellent work. I'm very encouraged to see that somebody's worrying about unoccupied vehicles. We've had lots of discussions about them, but nobody's really incorporated much analysis about the effect of the unoccupied vehicles. So this is really encouraging. Good stuff. Thank you very much.
Great. Thank you.
All right. Let's see. Our last presentation in this session is a social spatiotemporal graph convolutional neural network for human trajectory prediction by Christian Claudel. Christian's a member of our faculty here at UT. He is a sensor guy. He's actually got his terminal degree was in electrical engineering, I believe, from Berkeley. And we're really lucky to have him here on our faculty in civil engineering. Christian, please go ahead.
Thanks. Thank you very much. Let me just share my screen very quick. Share here. I hope you all can see my screen here.
Yes, indeed.
Oh, good. Okay, so let me just put in full screen now. All right, so thanks everyone, and thanks for the introduction, Randy. So what I'm going to present now is the social STGCN, so a social spatio-temporal graph convolutional neural network. That's the name of the algorithm that we have worked on for predicting the trajectory of pedestrians. So it's probably related also to the work of Wei that he presented earlier about predicting the trajectories of cars. So what we want to do here is to predict the trajectories of pedestrians, and this is a project that is motivated by the idea of improving the safety of traffic. So it's really the key idea here. Of course, traffic safety is important. We want to also improve the throughput of streets. And usually these are conflicting objectives, because if you want to improve the throughput of intersections or the throughput of roads in cities, you're taking more risks and you have more collisions. So our idea is to leverage the new technology based on augmented reality. So this is progressing very fast currently. There are lots of applications of augmented reality, particularly for construction management, and also for example, for the army. So there are new generations of goggles that are used now outdoors by soldiers for targeting and mission planning, etc. So this is something that is really that it really has a lot of potential. We believe that it also has a lot of potential for traffic safety, because if now you're walking in the street, or if you're riding a scooter or a bike, you are much more aware of your surroundings if you have information that is displayed around you about these people. So, for example, we have done some research with these Google glasses here, where we try to look right next to the ECJ building at UT. We just try to see how accurate we could target people and detect them. Of course, the Google Glass is very limited in capability. So we had someone carrying a tracking device, and you can see that here the tracking is not great, it's not perfect. So of course that was maybe 5 years ago. Now the technology has improved significantly, and we can do much better by fusion of images plus transponders and so on and so forth. So the idea is to use this AR and this augmented reality to guide people through intersections. And there is so if we look, for example, at a typical intersection setup, we have multiple types of users that can go through the intersection. So they can be pedestrians, they can be bicycles, they can be human-driven vehicles, and these are the classical things. And there can be also autonomous vehicles. I mean, in the future, right now we don't have any, but that can come in the future. And the idea is to improve the flows in a city, particularly at the level of intersections, which are major bottlenecks in cities, to improve the flow by having some intersection manager that would be able to send guidance information to everyone crossing the intersection. And the information could be sent, of course, automatically to autonomous vehicles, and that would be just an assigned path to go through. But for anything that is driven by humans, like vehicles or pedestrians, we need to provide the information in something that the humans can understand. So that could be, for example, go follow that path, or follow that lead vehicle, or some other visual way of providing information. For example, you could think that there wouldn't be any timing for crossing the streets. There wouldn't be any allotted time for the pedestrians to cross the streets, but instead you could cross the street anytime by just requesting to cross the street to the controller, and then the controller would slow down the other cars and let you cross the street. So that would improve the flow and the safety both. The problem is that there is some difficulty in the system. So this would work very well if everyone was controlled, so everyone had glasses or everyone was autonomous. But the problem is that we have also people that will participate to that, and a lot of them will not have these devices. So here we focus on that particular problem. How do we handle the uncontrolled people? The uncontrolled people, that's difficult because they tend to be able to do anything they want. And what you want, if you want to avoid collisions, is of course to predict what will happen in the future, because you have a current state of traffic, you have the current position of everyone. But what you want is to make sure that you can also know what people are going to do, what cars are going to do next, in order to avoid the collisions. So here, this is our focus. This is our main focus. And our idea is essentially to answer the following question. So given some images obtained of the scene around the intersection. So the images that can come from cameras, or they can come from LiDARs, for example, so they can come from a variety of sources. How can we, but here we focus on camera mainly. So based on these camera images and these videos, how can we know what people will do next in the future? So for example, over the next 5 seconds or over the next 10 seconds in the future. So here, this is something that is useful for, as I said, for the uncontrolled agents. That means that the people that won't be controlled, but even with the people that will be controlled, so even with people that will wear glasses, will have to also do the same activity, because they are supposed to follow a certain trajectory, but we know that people don't do exactly what they are supposed to. So we'll need to somehow understand how people react in order to predict, even if they were assigned a certain trajectory. So there are some difficulties that are associated with this prediction of trajectory. One of the difficulty conceptually is that if you're having a human, so if you're having an autonomous vehicle, it's probably easy to predict what they will do next, because you can somehow know what they sense and you can know what they detect. So that's a little bit easier, even though there are some surprises with that still, because for example, on an autonomous car, the car has a representation of what is around itself, but it can detect anything at any time. For example, some cross traffic or something that was not seen by the car can be suddenly seen, and so therefore that will affect the behavior of the car. For humans, now that's complex also conceptually, because we don't have good models of how humans evolve. We can have a good model of how a car evolves, because that follows the laws of physics. So we can know, for example, based on the torques that we apply on all 4 wheels, we can know the evolution of the car, the dynamics of the frame, and the dynamics of the suspensions, and all these things in a corner, for example. So all these things is very, very well predicted, and it's very easily predictable. However, humans are very complex machines, of course, and we have a lot of inputs, and we have our brains, and we cannot model what we think and what we decide. So that's the difficult part. We don't have humans model that are good, unlike the physical models of a vehicle, for example. So that forces us to rely on solutions based on machine learning, because we don't have any model to obtain. In fact, the problem is it's not really in terms of modeling. The problem is not so much the model of the human actions. If you, for example, if I add information on every muscle that I would move now, I would be able to predict very well how I would be later on if I had the information of which muscles will be actuated. The problem is, how do we predict what we're going to actuate in our muscles? So that's the problem of obtaining the inputs of the dynamics when we think about a dynamical system. The model itself is known, but the problem is the inputs. The inputs are completely unknown and they are unpredictable. So here, that's what we want to try to predict. And for this, as I said, we are going to rely on machine learning because we don't have a good way to determine this. It's really pretty much impossible to obtain a good model of what a human will decide in the future. So this is, of course, the subject of a lot of research in human factors, for example. Understanding how humans will react to a certain situation. This is, of course, something of interest for the community. For the case of pedestrian trajectory prediction, what we want is to try to use information from the video and somehow extract that information to predict what people will do. And the informations can be, for example, body cues, like, someone walking, for example, maybe might look at in some direction. So that body cue can be interpreted by someone that is looking at the scene that, okay, the person wants to walk in that direction. And of course, we'll need to make sure that the machine learning algorithm can have the same performance and can detect what the person will do next. So for this, we use machine learning, as I said, and we're going to use an algorithm that we call social STGCNN. So I won't describe it too much here for the sake of time. What I want to mention briefly is that this algorithm is based on artificial neural networks, and it's also based on a graph representation of the scene. So that means that we'll have the pedestrians that will be described as a certain graph. So there will be some edges between each pedestrian or between each user, and we'll have a certain function that encodes the interaction between these pedestrians. And over a single pass, so it's not a recursive approach where we need to re-estimate over time. Over a single pass, we'll predict what the trajectories will be in the future. That's the objective of the algorithm in a nutshell. So to address this, we model again everything as a graph. We predict over some horizon, and we're going to again describe a little bit more how the graph works. So we have a certain graph. So here you have, for example, 3 users, one in red, one in yellow, and one in green at different instants in time. And what we want is to model somehow the interactions between all of them. So we'll have the edges between the graph that will be representing our interactions, and we have a certain function here that is used to represent interactions between these people. So we have a function that is 1 over the norm of the distance, and so it's basically a very simple function that tells us that if you get closer to someone, you have more chances of interacting with this person. So that's the kernel function that we're using. And that's essentially the added part in our neural network approach. So we have also that all future positions are modeled as a bivariate Gaussian distribution. So we predict not just the next trajectory as we think it will be, but also a range of where the trajectories will be. So there is a Gaussian distribution of what the future paths of the pedestrians can be. So now in terms of inputs and outputs. So the inputs are going to be the images, the video images that we obtain from the scene. And these images are obtained from an overhead video camera. So they can be obtained from a drone camera, or they can be obtained from a camera that is overlooking the scene from a building, for example. We, of course, use the information from the past. So if you want to predict what people will do in the future, you need also to know what people have done in the past and to try to extrapolate from that. So what we are using in this approach is, I believe, a few seconds, like 4 or 5 seconds of data in the past, and then we try to predict what will happen in the future in the 4 or 5 seconds next. So we have the first part of the algorithm is to, of course, detect where everyone is in the frame, then regularize this information between frames and to make sure that we keep track of who is who along the frame. Then once we have detected the different people in the frame, we just detect the distance between each of them. So that's used for this kernel adjacency function. Then we use this graph convolutional neural network layer to represent the interactions between everyone. And we have some time extrapolator that also extract additional features over time. And that use in particular the fact that we have the interactions over a certain time in the past. And so we use that to predict the future. And as an output, what we get is the predicted distributions of the future trajectories of the users. For example, we had some trajectories up to a certain point, and what we do is we get these clouds of possible paths in the future. So you can get different outcomes in the future as well, because we have Gaussian outputs, but we also varying some parameters initially, and we are performing some sensitivity analysis to just determine what can happen, and you can have some splits sometimes in possible paths. So this is some example of trajectory computation. So you can see on the scene different images, the images that are used as an input. So we use these images. So here it's a little bit probably hard to see on my screen because I think I have the low contrast, but I think it's probably easier to see on your screen. So here you see the trajectories of the people that are there, 2 people walking together. So they keep walking there. And at some point, you predict what will happen next. So you predict based on what people have done in the past. This is their likely path. So here you can see that it's something reasonable, and they have been working in the up-down direction for a while, so they will keep doing that in the future as well. That's something simple, but you might have some situations that are a bit more complex with multiple users interacting. So now that's in a nutshell the way the algorithm works. So in terms of performance, we also wanted to validate this over some data sets. And for this, we use some standard validation data sets used in the machine learning community that were generated by some universities like ETH. And I believe Stanford University also has the data set. So these are data sets of pedestrians that are detected with some video cameras, and these 5 data sets usually they are the benchmark data sets that are used to test every algorithm and to compare every new algorithm. So to evaluate the performance of the algorithms, what we did is we used 2 metrics: the average displacement error, which is the errors in predicting the displacement of the errors in predicting the position of the persons as the trajectory is predicted. So we predict over a certain time horizon, for example, over 5 seconds. So the first metric is what is the average error that you are doing over the first 4.5 seconds. And then the last one is the FDE, the final displacement error. So what is the error that you got after 5 seconds? And that's also some benchmark metrics that are used by everyone in the field. We also evaluated not only the performance there, but also the number of parameters that were used by the algorithm in comparison with the state of the art, and the computational efficiency, so how efficient it is to compute the trajectory or to predict the trajectory. So these are the results that we obtained. So we tested again on these 5 data sets, and here what you can see is the average displacement error and final displacement errors for each of the data sets with different algorithms that are shown here. So all these rows correspond to the state-of-the-art algorithms, And the last one is the algorithm that we have developed for this study. So lower is better, and the bolded results are the ones that are the best available in the literature. So you can see that across all data sets, we tend to perform better than the others. So of course, sometimes there are a few exceptions, but in most data sets, we had very consistent and good. And even if we didn't get the best possible performance, we were still pretty close to the best possible performance. So in average, we get a lower 20% lower average displacement error and a 2% lower final displacement error with respect to state-of-the-art algorithms. That's for the error. And also, we didn't push our algorithm too much. And we wanted to just obtain some better performance, but we wanted also essentially to reduce a lot the complexity with respect to these algorithms. So we also compared in terms of complexity, what was the advantage of this algorithm in terms of reducing the number of parameters and reducing inference time. So these two things are very important because you want to predict what will happen in the future for the pedestrians, but you want also to predict that fast, because if it takes 5 seconds to predict what people will do in the next 5 seconds, it's too late when the results are coming. So we want to be extremely fast. And if you look at some algorithms, even on big computers, they take still 1 whole second to compute, to infer what people will do next. So this is really too much, because by the time that you get the result, it's almost the end of your, I mean, it's not the end of your time horizon, but it's already quite late. So here we got some average computational time of 2 milliseconds only. So that was sufficiently fast. Again, we compared all these computational time, 10 computers, obviously, but if you take a better computer, you can get something faster. But more importantly, the number of parameters is actually much less than what was used in the past in other publications. So it can be up to, I mean, from 10 to 50 times less in average parameters. So this is really something that's very helpful, because the less parameters you have, and the more you can predict. I mean, the more robust your algorithm will be. So here, I'm not going to describe, for the sake of time, also another thing that we wanted to evaluate, which is the machine learning. But this algorithm also tend to learn faster than the state-of-the-art algorithms, because it converges faster to the. I mean, it converges faster, and it also keeps getting. I mean, I believe it was for a very, very small amount of training, it already reached the performance of the next best state-of-the-art algorithm. So it's really learning very fast in comparison to other models. And that comes from the fact that it also has less parameters. So here, this is some qualitative analysis where we show also the advantage of the algorithm in getting more realistic trajectories. So on these examples, these two are two different versions of this algorithm that I presented you. And the third one is the next best in the literature, the SGAN. And you can see that if you look at these trajectories, for example, the trajectories tend to be more realistic. They tend to follow the path better than this, for example, SGAN that predict that people will turn right when in fact they keep going straight. And so you get the same issue here, for example, in which the path really don't contain, the predicted path don't contain the actual. And you also have something interesting that happens for interactions. For example, when people arrive, and so it encodes more the merging behavior. You know, if people walk together, so they tend to merge. And here, for example, for that algorithm, it tends to collide, and that's not what's expected to happen. Or when people are coming together, I mean, they are going in front of each other. In this case, they tend also to avoid each other. But this algorithm, the SGAN, was predicting that people would go straight and collide. That can also be extended to more complex situations where you have multiple people walking together and crossing the path of another person. So we have something also that's more realistic in this situation. That's not to say that it's perfect. There are some situations that are unrealistic, and that happens in all machine learning algorithms. It works with a certain percentage, but there are some fails as well, and the failures tend to be also spectacular when they occur. So I gave just a few examples here. For example, this is a situation where where are supposed to work together, but we predict actually that they will diverge a lot. And here the trajectory that is predicted is quite unstable when in fact people to stay together. So here that can occur, and that's also some topic of research, and we have to make sure that things are more. But of course, I mean, that's not just limited to us, but that's limited to any algorithm that is used for prediction or path planning for autonomous vehicles that's relying on machine learning. They all have the same difficulty. So just for conclusion, this work was the presentation of the social SDG CNN, so the algorithm that can be used to predict trajectories over a small time horizon using as input data, video data, so a few frames, predict a few frames in the future. The main advantages of this algorithm is that it outperforms state of the art, but also it uses much less parameters and it can be trained much faster than the classical algorithms. And again, it's based on the representation on the convolutional neural network that uses graph theory elements, so for the interactions. In future developments, what we're going to work on is to improve accuracy and the robustness to make sure that we have less of these crazy events that can occur sometimes. And also we want to extend the algorithm to partially control situations because if people now start to wear goggles or start to follow these instructions, they won't follow these instructions perfectly, but based on these instructions, we'll still have a good idea of what they should do next. So what we want is to predict by how much they will deviate from these. And the more we are able to predict these things well, the more we'll be able to make a safe environment with the autonomous vehicles and people. So thanks everyone, and that concludes my presentation. I'm ready to take any question you may have.
Thank you, Christian. This is very interesting stuff. You know, I recall years ago sitting on a committee of a doctoral student who was modeling pedestrian movements, but in situations where there was a very heavy crowd. In fact, he actually got data from the Middle East where people were visiting a holy shrine. Yeah. And it seems to me that process is much simpler than the one you're working on here, because the people themselves are limited in terms of how they can move by the people around them. So that leads me to a question here. I wonder, I guess at some point, the density of people per unit area, would approach the situation where people really don't have as much freedom as those do in your work here. And so I guess it would seem to me, I'm not sure this is correct, but it would seem to me that at some point, as density increases, the modeling process becomes simpler.
Yeah, I think so. I think there would be more interactions, more local interactions. I mean, this is also something that happens in robotics when people study robotics with local interactions and with potential. But that could become a bit simpler. However, the prime of this situation is also sometimes you have the stampedes and all, where you have, I mean, when you can have some disasters, and in that case, the modeling completely breaks down. And I believe predicting these situations might be pretty challenging. With our algorithms, I don't think we can do this thing at all, because it's designed really for small, not very crowded intersections where we have limited interactions between people. I believe that with a lot of interactions, this particular approach would fail because it would require too much computational time, because there would be too many adjacencies between every user.
Any other questions from anybody? All right, thank you very much, Christian. I believe, Wei, that's the last of our presentations in tech session number 2. And we're running a little bit behind time. I apologize for that.
Oh, no problem at all. Thank you so much, Dr. Machemehl.
Yes, sir.
I think we have a next one, which is 1:30, right? Start at 1:30. The student Lightning presentation session. So thank you all very much, and we'll take a 1 hour break, and we'll see you at 1:30.
Thanks, sir.
Thank you.
Bye.
Thanks.
Yeah.
Thanks.
Bye.